Okay, so now I want to finish, we'll finish our discussion of Markov chains with um, by talking a little bit about continuous time Markov chains. So far everything we've talked about have been discrete time. And so the main difference now is that, well, in discrete time, time was indexed by the positive integers. And in continuous time, we're going to allow time to be indexed by all positive real numbers. And so an example of this that we saw earlier in the semester was the Poisson process, where we allowed arrivals to occur according to according to the times of an exponential random variable. And so what that led to was a process that was indexed by continuous time, in continuous time by the positive real numbers. So in this case, we're going to let x be a process by the positive real numbers. And just to give a definition, x is a continuous time Markov process well, let me say continuous time Markov chain, so I'll still use that terminology of a Markov chain. It's continuous time Markov chain if its sample paths satisfy the condition that the conditional distribution of the state at some future time Tn plus 1 given the state at some collection of past times depends only on the most recently observed state, and also depends only on the time lag. So the difference in times given the initial state x. Okay, and so what we will write this as, by definition, will be transition probability Tn minus 1 from x to x prime for all finite collections of times. Okay? So that's the first condition. That's the Markov condition brought into continuous time, which is saying that the finite dimensional sample paths satisfy the Markov property, just as we saw in the discrete time setting. And in continuous time, there's an additional technical constraint saying that the sample path is CAD lag with probability 1. And what this means, so CAD lag is a French acronym. Sometimes you'll see this as written as RCLL, which is the English version. And what this means is CAD lag means continuous, write it this way, means right continuous and left limits. Okay, so all this is really saying is this is a condition that since time is evolving in continuous time, this is the requirement that if the process is evolving on some state space, say x, then state starts somewhere, it holds for some amount of time in that state, and then it jumps to the next state. So all this is saying is that we have limits from the left, meaning that this limit exists at this point here, the time of the first jump, and continuous from the right, meaning that we do hold for some strictly positive amount of time. It could be a very small amount of time, but we hold with probability 1. And so what this is preventing is the possibility that this process jumps infinitely often in some arbitrarily small time interval. Because if that were to happen, then the process would not be well behaved. And so what we can do, well, first of all, an example of such a process that we've already seen and that I already mentioned is a Poisson process. And a non-example in general of a process that we've already seen is a renewal process. So in the Poisson process, this sample path over here could very well be the jumps of a Poisson process. So this would be the counting process n of t, and that has the Markov property, which you could show by the fact that the holding times in a Poisson process are memoryless; they're exponential. But in general, in the renewal process, we don't require that the renewal times are exponential or memoryless, and so the Markov property wouldn't hold. So what we would like to do is show some general structural properties of continuous time chains, and a lot of it follows from what we already know about discrete time chains because of the definition of this continuous time Markov property. So this is the Markov condition here. And so what we can do is we arrange, so let's write PT to be the t-step transition matrix for each t. And I'll just note here, which we'll make use of later, which is that P0 is just the identity. So this is the identity at x. Meaning that in a time of time interval 0, in a time of length 0, we don't make a jump. We stay where we're at. Okay. So first thing that we want to do is we want to make the connection between this generic structural condition that we've described here and what a process satisfying the condition might look like. We've already given an example of a Poisson process as something that satisfies this condition. Are there other processes that satisfy it, and what general properties might they have? Okay. And so the first thing that we can consider, as we did in the one of the first things that we consider is, well, how long, or what is the distribution of the first jump in this chain? So we have a state space x, we have time evolving continuously, and we assume that we start in some state at time 0. We stay there for some amount of time, some random time, which I'll define as Tx. Tx is the minimum, or no, the inf, since we're talking about continuous time, the first time point t at which the chain leaves state x. What's the distribution of this waiting time? Oh. So how are we going to prove this? Or, well, how are we going to, so what is our intuition for this? Well, some intuition that we might have is that we do have to have a, what happens in discrete time? So we actually didn't study this question in discrete time. What's the distribution of the holding time in a state in discrete time? Assuming that, so in discrete time what we have is a process that's indexed by the positive integers. And let's say we started in state x at time 0. So then the question is, well, what's the distribution of our holding time in state x in a discrete time process? Well, there's some jump chain or some transition probability, and the probability, so we can ask, well, what's the probability that the state at time 1 is not equal to x, given that that we started in state x? Well, this is just 1 minus the probability that we stay in state x for a single jump. And so the question is, well, how many of these jumps does it take for us to leave state x? Well, in this case, in discrete time, we know that in a time homogeneous chain, the probability of leaving is the same for all such values. Think of that as a success probability in a geometric process or a Bernoulli process. And so the waiting time here must be geometric in a time homogeneous discrete time Markov process. Okay. So one thing that we can see then is that in a discrete time process, the waiting times are always geometric. So they have the memoryless property. We know that the geometric distribution is the unique distribution on positive integers that is memoryless. And so we might suspect, since we've already observed that the Poisson process is a continuous time Markov process, that we also require, it's also required that the waiting times in a continuous time process are exponential, memoryless. And so this is our first theorem. So for all x, there exists some value lambda bigger than 0 such that the time of the first time we leave x in the process is exponential with rate lambda x under initial distribution px. So assuming we started in x, the first time that we leave x, first time that the chain is not in x, is exponential. And the way that we're going to prove this, I'll sketch the proof here. Really, I already sketched it by showing that the discrete time chain, the first jump time in a discrete time chain has to be geometrically distributed. What we can do in continuous time. So for the process, so fix x in the state space, and for each m, so for each integer m, break up the positive real line into increments of size 2 to the minus m. Okay, so what I'm going to do is I'm going to take time, and in discrete time we saw that time was already broken up into unit increments, but in continuous time we can do something similar, which is we can break time up so that the time increment is of length 2 to the minus m, so on. And so now the question is, given that we started in state x, we want to ask, what's the chance that we leave that state in increment of time 2 to the minus m? So we end up with a Bernoulli process, so we can define random variables y sub, let's say, k, to be equal to the indicator that x at time k 2 to the minus m not equal to x. And the question is, let's define t sub x m to be the first time the minimum value at which yn equals 1. Okay. And so by the argument that we had already given, we know that this distribution is geometric by the Markov property. The Markov property holds for all finite sequences, for all discrete sequences of time, as we defined here. And so this is going to be geometric, and the success probability is going to be 1 minus p 2 to the minus m xx. Okay. That holds for each m. Now it is possible, of course, that in an interval of time 2 to the minus m, we actually leave x, and then we jump back to x by the time 2 to the minus m happens. So we don't observe that leaving time. So we have to show that, first of all, txm decreases down to tx as m goes to infinity with probability 1. And then we can use a lemma, which is related to something we've already shown previously, which is that the limit, we can express the limit of a sequence of geometrics, and it does turn out to be exponential. So if we let g1, g2, etc. be some sequence such that gm geometric pm, and the decreasing limit 2 to the minus m converges to some random variable with probability 1, then that random variable is exponential with some rate. Okay. And the proof of that is in the notes. I won't go through it here. Okay. So what this tells us is that the behavior of a continuous time chain can be described, first of all, by a holding time, but then once we hold for some amount of time, we know that the chain has to go somewhere. And so that the jumps of the chain can be described by a jump matrix, which I'll write as A sub xy. So we have a jump matrix A sub xy, which is the conditional distribution of the probability of where the chain goes at the time t, probability that we jump to time t, given that we started in state. We jump to state y, given that we started in state x, where t is defined as the first time, the stopping time of the first time at which the chain leaves state x in this case. So the structure of a continuous time Markov chain is pretty straightforward based on this. What we do is, given that the chain is in state x at time t, we first generate time tx to be exponential with rate lambda x. We define x t plus s to be equal to x for all s up until time tx, and then we define, or we generate the new state x t sub x from the jump matrix A. Okay, so what this allows us to do is, so intuitively what's going on is we have this picture of the process. We're in a state x. We generate the waiting time t, and then we generate the next value according to some probability, axy, and we repeat. Okay. This allows us to summarize the structure in terms of what's called a Q matrix. So in the discrete time case, we described the structure of a Markov chain by what's called its transition matrix, transition probability matrix, and that was enough to describe the whole process. In continuous time, we have a little bit more structure in that we first have to, so we have the waiting times and we have the jump probabilities, but we can summarize the behavior of x by what's called a Q matrix. And what the Q matrix is on the off-diagonal entries. So the off-diagonal entries tell us what is the rate at which we jump from x to y. And the diagonal entries are actually negative the rate of the total rate at which we leave x. So in the discrete time, in the continuous time case, we no longer have a probability of staying where we're at. Once we decide to make a jump, we always jump somewhere other than where we're at. And the only question is how long we hold in a given state. And so something to note here is that this is no longer a stochastic matrix, but it is a matrix for which the rows add up to 0. Okay, so the first main theorem that we can show actually in the case of um, continuous time change is what's called the Chapman-Kolmogorov theorem. So remember, so recall that we had in the discrete time setting the Chapman-Kolmogorov equations. For discrete time chains, the m plus n transition probability from x to y could be expressed as a sum over all intermediate states of going from x to z in n steps, and then from z to y in the remaining m steps. So the rationale there was pretty clear from just the structure of a Markov chain. If we're in state x, we want to get to state y in exactly m plus n steps. We know that we have to be somewhere after, well, just to be consistent, let me say, talking about m plus n steps, we have to be somewhere after m steps, wherever that is. So that's going to be a state z, anywhere in the state space. And then wherever we are after m steps, if we want to get to y in exactly m plus n steps, we have n steps to get to y. And so that's all that's saying. What the Chapman-Kolmogorov equations now generalize to in the case of, or extend to in the case of a continuous time chain, is an expression in terms of the Q matrix. So the Q matrix is describing the infinitesimal jump behavior of the chain and I'll call this the Chapman-Kolmogorov theorem. So this is the Chapman-Kolmogorov theorem for continuous time Markov chains. So let's let PT xy, let's let this be the Markov semigroup, or the T-state, T-step transitions probabilities, transition probabilities for all T. Okay. And we have two equations from Chapman-Kolmogorov, which talk about the derivative. So the derivative of the chain of the t-step probability of going from x to y in t steps, is given by the sum over all intermediate steps z of this expression qx z pt zy. This is called the backwards equation. And alternatively, we can also express this derivative as going ptxz qzy, which is called the forward equation. All right. So what this is saying, first of all, in terms of in terms of matrix notation, so in matrix notation, the matrix with entries given by the derivatives of PT can be expressed as just the matrix product QPT in the backwards case, or PTQ in the forward case. All right. So before we prove this, the intuition actually follows similarly to what we saw in discrete time for the Chapman-Kolmogorov equations, and actually the proof uses the Chapman-Kolmogorov equation as well. But what we're doing is we're thinking about the Q matrix as the infinitesimal probabilities. So we can think about so in the Q matrix, what is the probability of jumping from infinitesimally small amount of time? And that's going to be given by the matrix, given by the entries of the Q matrix. Okay. So if we think about it in those terms, if we're going to make a jump from x to y in t steps, what we can do is we can think about moving from x. Well, first we can think about making an instantaneous jump from x to anywhere else in the space, and that space could also, well, so we make a jump from x to anywhere else, which is given by this q, and then once we're anywhere else, we just have the usual t-step transition probability. Or alternatively, for the forward equation, we could jump from x to anywhere else in the first t units of time, and then at the last moment jump from wherever we are, z to y. Okay, so that's the intuition, and that's essentially exactly how the proof follows. So the proof is to consider, let's just assume for the time being that x is finite, to keep things simple. Then what we have is that by the Chapman-Kolmogorov equation, we know that we can express the difference. So what do we know? Well, what we know is that the probability of going from x to y in t plus epsilon, so if we think about for epsilon bigger than 0, probability of going from x to y in t plus epsilon amount of time by the Chapman-Kolmogorov equation, we can write this as probability of going from x to z in epsilon amount of time, and then from z to y in the remaining t units of time. That's the discrete time version. So that will be satisfied by the continuous time chain just by definition. And so what this allows us to do is we can write the difference of the probability of going from x to y in t plus epsilon and going from x to y in t units of time is a sum. This overstates x, states z. This is a sum of what we've already seen up here. But what we can do is we can pull this. What do I want to do? So I can write this as PTZY times P epsilon xz, so that's just the first term given by Chapman-Kolmogorov, minus the indicator if x is equal to z. Okay, so that's just what we need. And if we want to compute the derivative, we have to consider dividing by epsilon in this case. So we divide by epsilon, so in order to prove this, we need to show that the limit of 1 over epsilon dt epsilon equals q of x z as epsilon goes to 0. Okay. And now what we can do here is we want to show that the limit, first of all, is, what's this? So the probability, so consider the probability of going from x to y in a very small period, in a very small amount of time, which is what we have here, right? What we first show is we consider the fact that the first jump time of the chain, or the first jump out of state x, is exponential with some rate lambda x. And so if epsilon is small enough, the probability of going from x to z, where z is not equal to x, probability of going from x to z in a time increment of epsilon is going to first require that we leave x at all. And so we first consider the probability that t1 is less than or equal to epsilon, which we know is 1 minus, this is just the CDF of the exponential, and we're going to take epsilon to be very small, so we can approximate this by some kind of by a Taylor expansion very easily. So this is 1 minus lambda x epsilon plus little o of epsilon squared. Okay. And so what we see is that this is lambda x epsilon plus little o of epsilon squared. And furthermore, that the limit as epsilon goes to 0 of the probability of jumping from x to y is going to be equal to, well, in order to jump out of x, we have to first jump out of x, and then we have to jump from wherever we are, which is x, to y, right? So this is going to equal the probability of jumping, of leaving, first leaving x, and when we do leave x, going to y. Okay. Need a limit. And the reason that's the case is that we know that if epsilon is small enough, we're only going to make at most one jump in a very small period of time. But this limit here, so this has to hold for epsilon bigger than 0, but what we want to do is we take we're looking at the derivative, so we divide by epsilon, and what we have up here if we divide by epsilon is that this is equal to, this limit is equal to lambda x axy. So in particular, and also we know that the limit 1 over epsilon p epsilon x x minus 1 is just the limit of the probability of leaving x, or negative of the probability of leaving x, which we know is negative lambda x. So that's the argument for the case of the forward case, and the backward case is the same. So the backward case, the other case is exactly the same argument. We just use the Chapman-Kolmogorov equation again, but instead of epsilon here, we use the epsilon for this jump, and we do the same argument. Okay. So the last thing I want to talk about for see how much time we have here. So the last thing I want to talk about for continuous time chains is their convergence to stationary. And I'm going to go through this pretty fast just to give some intuition so that we can move on to the next topic. So in discrete time, we already know that pi is stationary if and only if pi p equals pi. So if we start in pi, if the distribution of where we start is according to pi, and we take a jump, then we're still marginally in distribution pi. In continuous time, this relationship is still going to hold for arbitrary values of t. But what we want to be able to do is we want to be able to describe the transition behavior of the chain in terms of the Q matrix. So rather than having to verify this for all values of t, although it turns out that if it holds for one value of t, then you could show that it holds for any value of t. And that's one of the nice things about continuous time chains. But since that's true for all values of t, that's what allows us to just prove it in the case of the show that it's satisfied for the Q matrix. Okay. All right. So how do we do this? Well, the first thing is I just want to make a proposition. So what's going on here is if we let x be a continuous time chain, with Q matrix given by this, with some Q matrix, then we have a stationary, then pi is stationary for x if and only if pi q is equal to 0. All right, 0 sub x. So where 0 sub x is the length x vector of all zeros. So what does this mean? So if you think about so this is saying that the stationary distribution pi, so if we start in pi and then we take a jump, an infinitesimal jump according to Q, that we don't actually go anywhere. Okay, so that's maybe a little bit of intuition for what this is saying. And the way that we can prove this, so very, very quickly, is that the proof just follows from the Chapman-Kolmogorov theorem. So in the Chapman-Kolmogorov theorem, so let's see. So first of all, what we know is pi t. Not that right there. So what we know is that pi pt is equal to pi. So assume that pi is stationary. Then pi pt is equal to pi. Okay. And pi t, this is true for all t. So for all t. And we can take the derivative and evaluate at t equal to 0. But we know that pi doesn't depend on t, so that derivative is equal to 0, is the vector of all zeros. Those transition probabilities are not affected by t. But this here, this statement here, is actually just exactly d dt of what? Well, by Chapman-Kolmogorov here, we have that d dt of pt is equal to q of pt. So this is equal to, so d dt of pt is equal to q times pt, so it's pi q pt evaluated at t equals 0. But t equals 0, at t equals 0, pt is just the identity as we discussed earlier, so this is just equal to pi q. Okay. So this shows the forward direction. Okay. So then conversely, if we assume that, so assume that pi q equals 0, well, the first thing that we can do is we can just compute that pi q pt is equal to 0 pt, which is equal to 0, 0x, 0x. This is for all t. Okay. But we can substitute in by the, again, by Chapman-Kolmogorov, by the backwards equation, qpt, this is the derivative of pi pt, okay, which is going to equal 0 for all t. Okay. So what does this tell us? This implies that this tells us that pi pt is constant for all t, and we also know that p0 is the identity, tells us that pi p0, so the special case that t equals 0, is equal to pi, which means that pi pt equals pi for all t, which means that pi is stationary. All right, and finally, I will just record this statement here. So convergence to stationary for continuous time. Markov chains. So first we're going to define that in the continuous time case, x is irreducible if there exists some time t such that the chain has a positive probability of going from x to y for all x and y. Notice that periodicity plays no role in continuous time case because we can make jumps in any continuous time, but in any amount of time, and so there's no periodicity. But actually, what we observe is that something much nicer happens in continuous time, and that continuous time chains are a bit better behaved in the following sense, is that if we suppose that there exists a time such that there's a positive probability of going from x to y in t steps, then there's a positive probability of going from x to y in s steps for all s bigger than 0. And furthermore, if the chain is irreducible, then pt x prime y prime is strictly positive for all times for all x prime y prime for all t bigger than 0. And the proof of this is, so to prove this, we just observe that what does it mean for, well, first of all, since it's irreducible, that means that all states communicate. So if there's a way from getting from x to y, we know there's a way from, there's some amount of time in which we can get from any state to anywhere else. And what that meant in discrete time was that there was a path from any state to anywhere else with positive probability. But since we're now working in continuous time, is however much time it took us to take that path, we can squeeze it into an arbitrarily small interval. So if there's a positive probability of going from x to y in time t, then we can think about just rescaling the process down to fit into any arbitrary time epsilon, a strictly positive amount of time epsilon. And that's what gives us this statement. And so from this statement, we actually observe that irreducible chains in continuous time, and I'll just observe this here, in continuous time, our main statement is that a stationary distribution exists, a unique stationary distribution exists for all irreducible continuous time Markov chains, and that and in fact, if an irreducible continuous time Markov chain has a stationary distribution, then it's unique and it satisfies this limiting statement. And the proof is in the notes. The proof follows similar techniques to passing through what we know for discrete time chains. And so we pass through what we already know for discrete time chains, and then we go to the limit, okay, for arbitrarily small periods of time.